All right. We'll have a bonus video about that.
Wonderful.
Okay. So, I wrote down some stuff about the homework. I didn't write down the questions, but I wrote down, like, some answers. Oh, okay. So, the first one you had to do was in the chapter, right?
Yeah, it's the one about air conditioner.
Yeah, so we talked about that.
Mm-hmm.
Yeah, okay. So we talked about that on Saturday. And then I wrote down that there was one about when you lose weight or something.
Where does their 10 kilograms go? Doesn't
Okay.
it just go into fatty acids and beta oxidation?
Well, how does it leave your body?
Your energy expenditure? Technically, it gets converted into like ATP and FADH2 that you use for energy when you like run and stuff like that.
Sure, but then how does if you sealed your body in like wax?
Okay.
And then
we just really took it to another realm.
No, okay, wait. Not sealed your body in wax. Let's say you captured all of the.
Like
The thing is, I know what the answer is.
CO2
Like,
and
I know
water.
what the answer key says. So I'm trying to make that an
Talking
organic.
about, like CO2 and water.
Yeah. Basically, it's you breathe it out.
Yeah,
That's the
CO2.
big thing.
Okay, so CO2 and water.
Yes, and because you take in oxygen, whatever. But
But
so the thing is, what they want you to do in the answer key. So I like how we're pretending that like I'm helping everyone with the homework. I'm just talking about the answer key.
that's fine.
But according to the answer key, which it does not mean anything. Like it doesn't, it wants you to calculate
I prefer my answer.
if a breath is 500 milliliters,
What?
then you can find. So I'll just tell you, we don't. I'll say this, and we're not going to do it, but I'll just say it. They want you to find the mass of CO2. Sorry, 500 milliliters and 5% CO2. So apparently, you're supposed to look these up. That an exhalation. So this is one out breath.
Mm-hmm.
Is 500 milliliters, let's say, and it's at 5% CO2. Therefore, you can find the actual mass of CO2 that's in the breath. And then they want you to find.
How many breaths it takes to burn 10 kilograms?
Well, yeah, probably. Well, the other thing they said is find the mass of O2 in 500 milliliters. Again, a breath, but this is at the atmospheric concentration, which is, I think it's 14%. 40% O2. Now, the important part is that O2 has a molar mass of 16,
Mm-hmm.
whatever it's called, and CO2 is like 30-something, 44. So even though obviously there's much less, perhaps the mass, you can kind of see that the mass of this is going to be bigger. Like the actual amount of mass in an out breath is going to be bigger than the amount of oxygen, the mass of oxygen in inhalation. Of course, nitrogen doesn't do anything.
Mm-hmm.
Where I guess we don't worry about water, even though obviously you do exhale water from metabolism and stuff. What is it? It's like O2 plus
C6H12O6?
this kind of thing, something like this, with plus or minus a few to these.
No, you're right.
Oh, is this right?
That's
Okay.
glucose.
Glucose. Okay, yeah, and then you convert it to this is like metabolism or whatever, right?
H2O.
Yeah, so this is how you lose weight, basically. The point is that this is kind of weird because you can't really get this from the question
Yeah.
or for the chapter,
That's not what
but
I
it's
thought.
actually a true sort of fact.
I thought he was asking about like base metabolic rate. How
Yeah,
long does
yeah,
it
yeah.
take you?
I guess not. But this is actually a thing that people don't know. I feel like you'd think that how you lose weight is like using the restroom, for example.
Okay.
You'd think that's how weight, like if you plot your weight over time and you've been losing weight,
Mm-hmm.
where do you think it goes? And it turns out that most of the mass, like the metabolic, because when you lose weight, as you were saying, it's like a metabolic process.
Mhm.
It's not like the fat is like, being exited out of your body,
Okay.
right? It's not. It's literally being burned and used for metabolic processes, and all of the metabolic processes are
Okay.
going into here out of your breath.
All right.
It's actually very similar thing is that trees or plants
Mm-hmm.
kind of roughly go. They don't.
They pretty much do.
Yeah, and this obviously this is like a maybe.
That's
It might like cellulose or whatever is like probably different, something like that, right?
yeah. It's
Anyway, whatever. It doesn't matter. The point is that it takes in CO2
mhm,
and it gives off oxygen and then whatever.
and H2.
Oh, okay. So plus or minus. I don't know. That's not how these equations work. But anyway, so what was I gonna say? Oh, so trees actually get most of their mass, actually almost all of their mass from CO2
Mm-hmm.
because there's C here and there's H here and there's O here and they get water and maybe they give off some water too. But the point is that you'd think they grew in the ground, and so like, well, the ground is made of dirt, and like trees are like, it's probably made of mostly like dirt kind of stuff. Like I know there's not, no one would actually say that, but like perhaps you might, if you never thought about it, you might think that, well, obviously trees they get their mass from like the ground, right?
Nutrients, yeah.
But they don't really. They just get like bits and pieces of stuff they need from the soil.
Mhm.
But they get their actual mass, like 99% of their actual mass
Mhm.
comes from the CO2 in the atmosphere and then water from the ground and from
Right.
wherever. And they give off, anyway, whatever. They give off this, and so anyway, whatever. The point is that using the fact that your in and out breaths are this much volume, and they want you to practice, I think, computing, well, if there's 5% of this is CO2, then you have, this divided by 20, whatever that is, milliliters of CO2. You can convert that if you know the density, I guess, and the molar mass. You could find the mass of that CO2.
Mhm.
And then therefore you could find mass in equals something, and then mass out. And mass in is CO2 and mass out is oxygen.
Mhm.
And then you could supposedly subtract them and find the net mass.
Wouldn't mass in be O2 and mass out be CO2?
Yeah, sorry. Yeah. I was thinking of trees. Yes, you're right. Of course, yeah. So mass in would be, O2. And mass out would be CO2.
Mhm.
Anyway, and then you could subtract them, and then it says that's how you lose weight.
Okay.
But obviously, it's a little bit of a stupid thing to do because, I mean, I don't know. I guess if you really want to do the question, what I'm saying is that you don't actually. What I would like people to do for this question is just find these masses.
Okay.
So, given a breath of 500 milliliters, 5% CO2 in your exhalation, percent, and 14% or so oxygen. If you look it up and it's something else, just do something else, whatever. About 40% oxygen. What is the mass of the CO2 you give off, and what is the mass of the oxygen you take in?
Mm-hmm.
And that's it. You don't need to do anything. But the point of the problem was to subtract them, and then I guess how you'd really do it. I don't really think the answer key does this. How you could do it is just find what percent. If you're losing this much weight, let's say you're losing 10 kilograms in a month,
Mm-hmm.
then you could do some computations to figure out how many breaths you breathe out in a month, and then you could kind of reverse this and compute the percent of CO2. It might be 6% CO2.
Mm-hmm.
Like if you breathe out 6% CO2 for a month, it's could be because you've lost weight, right? Like your body is in the process of losing weight. I guess. Obviously, this is all based on like 100 approximations that are not correct. So that's why I thought this was kind of a silly problem. I would just say, just find these masses. It's just a practice. This is the only thing you need to do this part
Mm-hmm.
is just to know the molar mass. This is grams per mole. Is that right? Grams per mole, and you can convert from moles to liters using PV equals nRT, I guess, right?
Mm-hmm.
nRT. So N is in moles, R is a constant, T is just atmospheric, like 298 or 300, whatever. P is atmospheric pressure, and you could find the volume. Yeah, there you go. So then you could use PV equals nRT. So the only thing you need to use are, this is molar mass, which I don't know what the symbol is for. We don't really have one. Anyway, whatever. And then PV equals nRT.
Mm.
So I'm not going to do it, but just like put these together, and you should be able to figure out a number in kilograms in one breath. Let's say, if you want, you can multiply it by whatever, how many breaths in a day, and figure out in a day how much weight and stuff. But I just want you to. I don't want you to like skip the problem because obviously it's a homework problem. But
Mhm.
I don't think it's reasonable for you to just do all these stupid approximations and then get like a nonsense answer. So
Appreciate
this is the important part, I think.
Cool.
And again, it's just to make sure you know how to use these molar mass things and go to volumes using PV equals nRT, I guess. So yeah, that's it. Okay, that's number 5.
Yeah.
Okay, what was number 6? Was that the one about the?
Cloud formation when you open a beer bottle.
That's right. Yeah, that's it. So so those are just examples where they want you to just explain it, right?
Yeah.
Okay. So when you open a beer bottle, the thing he's talking about is the fact that this is. I'm gonna draw a picture so that. Also, let's just say that you open a can because I feel like you see it way more when you open a can. Maybe you don't. I don't know. That's not really what a can looks like, but.
Close.
I don't. Anyway, okay,
It's fine.
whatever. You open a can, and it's like there's a little cloud above it. Looks like it exploded. Anyway, you know what I mean. You open a can, and not of course, when you first open it, it's carbonated, so it's gonna like spray and not spray everywhere, but like makes a little,
Yeah.
right? Not that. That is not. So someone in class literally said that. I think that this is where I'm trying to just reverse confusion.
Great.
Because in class, someone made that noise,
Mhm.
and everyone laughed because that's how it sounds. It's very funny. But that's of course from the CO2. And this is not to do with CO2. The thing he's talking about with the cloud is not the CO2. He's talking about like the vapor, the sort of white, cloud, basically like fog that you can see coming off. Or yeah, I guess you can see it in a beer bottle.
And then like neck of the bottle.
Right, you can kind of see it in here. It's like a little cloudy, right? So here's the liquid.
Mm-hmm.
I shouldn't have written the same. And here, maybe it's a little cloudy.
Right.
And then maybe it kind of comes out a little bit when it's cold.
Right.
This will only
When the mountains
happens.
are blue.
Huh?
When the mountains are blue.
When the mountains are blue. When it's cold. Yeah, there's a funny. You know who David Cross is?
No.
He plays. I think his name's David Cross. He plays Tobias on Arrested Development.
No.
Oh God. Anyway, he has a thing about
You're out of my lines.
this thing. It's not a very. I wouldn't recommend it. It's not that funny.
Okay.
But he has a thing about the mountains are blue. He's like, of the 5 senses, when I want to know if something's cold. Anyway, okay. So the point is that Arrested Development is much funnier than him. You should watch. Also, this is a recommend. Everyone should watch Arrested Development. It's the funniest thing. It's the funniest show. I know it's like it's over 20 years. It's like 20 years old now. But anyway, let's get back to. So this is like a little bit cloudy or whatever, and then there's some. This only happens when these things are cold,
Mm-hmm.
and that is because the water, the atmosphere has some water vapor in it. It's H2O, vapor or whatever you call it. Is that how you write it? V?
G.
G for gas. That's fine. Thank you. So you write it like it literally has water vapor. It's not like it only has water vapor when it's raining or something like that. It always has some water vapor. I mean, unless you're like really in like the desert or something, maybe it has very little. But anyway, that goes in here, gets cold because it's in here. It doesn't happen when you have like a big, like if you had a bucket of cold water, you probably wouldn't see it because the water, the air containing gaseous water can just kind of flow around. It's not going to get in here. It gets kind of trapped and gets cold. So the air in here is cold, and so the water vapor actually condenses into liquid water. So the cloud that you're seeing is H2O liquid, right? It's actually liquid water. You cannot, this is invisible. And this is visible.
Okay. So it's like a legitimate cloud.
It's a legitimate cloud. A cloud, of course, a real cloud. You look up in the sky and it's blue. That's because all the water vapor that's in the sky, which there's plenty of, you can see right through. It's transparent. This is completely transparent. Liquid water and solid water, of course, is also visible. The reason I point this is obvious. It's ice is visible, but I point it out because clouds, some of the clouds are actually made of ice. They're little ice crystals, right? They're of course, the water vapor in the air went to a liquid first and then to solid. It didn't. You could skip. That's a thing, but it doesn't usually happen in the atmosphere. I don't think. Well, maybe it does. I'm not really sure. But anyway, these are visible. So if you see things that are made of water and you can see them with your eyes, and they block things like clouds do, then they must be liquid or solid. So the point is that in cans and in bottles, when something's very cold and the glass is cold, water or air gets trapped in there. Kind of, it can't just flow out. It gets trapped in there, and the air gets cooled down from the glass surrounding it and from the liquid, and then the water vapor starts condensing. Anyway, I think I've sort of beaten this into the ground, but anyway. So yeah, it has nothing to do with the carbonation. This will not. This won't happen for anything that's warm, that's room temperature, and it also won't happen. It'll still happen even if you have a can of something that's like not carbonated, like V8. Isn't that a
okay?
Like I'm just making what's in a can that's not carbonated. I don't even know.
I don't know.
I don't know why I think of V8. I've never had V8.
V8 is a very specific example.
That's the first thing I thought of when I thought of a not carbonated.
I couldn't tell you what's in a can. That's
They
not
have like
carbonated.
brisk iced tea, right?
Oh, that's true.
So anyway, that'll do the same thing if it's cold. Anyway, the point is that what's in a bottle that's not. Anyway, who cares? Yeah, okay,
Twisted
there you
tea.
go. Twisted tea, there you go. A lot of good examples.
Yeah,
there.
great. Just ripping them off.
Great influence. Okay, so great. Now, what was the second one?
The second one is you're blowing hot air or cold air out of your mouth. Blow hot
Yeah,
air,
okay,
cold
so
air
that
out
one's
of your
slightly different. I'll leave this up because the mountain thing is like similar. But yeah, so as he said, when you blow, if you have like hot air, your body is hot,
Right.
and your lungs are very warm, body temperature,
99.6.
and
98.6.
the air is in it, and so even though you breathe in and breathe out pretty fast, it still warms up, and so the air coming out of your mouth is hot. However, if you put hot air through I'm not even going to try to draw a mouth, so this is not a mouth, this is just like a balloon with a hole in it, and then it starts to spray out, right? The pressure here, the pressure in here, if you're squeezing it, if you're putting pressure on it, pressure is high, and then pressure is lower. And if pressure goes down, then temperature goes up, assuming that everything else is fixed. If we look at PV equals nRT, we can see that, actually, sorry, don't worry about pressure. Or, sorry, what do I want to say?
Temperature's supposed to go down.
Oh, sorry, temperature goes down. Yeah, you're right. I was like, that's ridiculous.
Yeah,
Yes.
so pressure is high.
There we go. Pressure. So the pressure and temperature, as you can see, as long as these are constants, if this goes up, this must go up. They're proportional, right? That's what it. P and V are not proportional. They're inversely related.
Right.
T and N, let's say, are that's a stupid example. T and N is not a really thermodynamic variable. Anyway, P and T and also V and T are proportional, and then these are the opposites. And so as the pressure goes down, which is atmospheric pressure out here, the temperature will go down as well. Yeah, that's it.
Okay.
So that's the whole thing. And of course, if you breathe out like this, you're not really doing anything with the pressure, so the temperature's not going to change that much from eventually cool down in the air. But yeah. Okay, and then there was a thing about the mountains or something, right?
Yes, the desert effect.
Oh yeah, so if you have
One side is covered with vegetation, the other side has none.
right, so if you have like the Rocky Mountains or whatever, most in the northern hemisphere, most of the air generally goes from east to west. Oh no, sorry, west to east.
Yes.
Sorry, I drew it, yeah. And because this is north. Okay, there we go. I will draw it in the standard cartography way. Anyway, so then you have this is a mass of air. This is not a cloud. Sorry, I shouldn't draw like that. I should just draw nothing here. This would be let's just say it has 50% water vapor. Right? This is I'm just picking it's not like high or low. That's actually a little high, but let's just say that's a normal amount. As the wind and just air pushes it up the mountain, right? Up here it's colder, and also the air pressure is lower. But we're just worried about being colder right now. Well, okay, fine. If air pressure is lower, so temperature is going to go down.
Well, the next question is, why is it colder on top of the mountain than it is at the bottom?
Okay.
So we can answer that in the next one, I suppose.
Okay, I'll give a separate reason for that, though.
Okay.
Even though you're right that they seem like they're the same.
It's like kind of similar.
So what I was going to say, I guess I don't really need this. What I was going to say for the next one, which is about why is it colder here?
Right.
I don't think that you could.
He's not looking for like.
Okay, let's forget about pressure. The reason is because I think if you solve PV equals nRT and you solve for the actual air pressure on a map like in the Rocky Mountains, so it's not like Everest,
Right.
right? But it's still like this could be like Denver, right?
Mhm.
It's not that high, so people live there, and this could be like sea level or whatever. I think if you solve for PV equals nRT and you solve for the temperature difference, it will not be that much lower.
Based on pressure.
Because it's definitely not just the air pressure. I was trying to just use that as an. Yeah, I shouldn't have said that. That's not correct. I don't believe that is the cause. So the pressure difference, it might be some of the cause, but it's not the primary cause. The primary cause is that it's just colder, which I'll talk about in a second.
Okay.
It's colder, and therefore the gas water vapor will condense to liquid water vapor. Someone's calling me. Someone from Argyle, New York. Sorry, let me just. Hello? Yes. Yes, it is. Good. I'm kind of in the middle of something. Is this, I just talked to someone about this the other day, actually. I think we're all set, though. About an offer? Okay. I think I'm all set, actually. Thanks, though.
There you go.
Comcast again. Okay. You sound very genuine.
So it's liquid.
Yeah, so it's liquid. Yes. So then it's liquid, so it's a cloud.
Right.
So it doesn't mean that it's going to rain necessarily. It could eventually, but then
It's
as you
visible.
go over here, now this cloud here, as it descends, it turns back. All the liquid turns back into vapor.
Mm-hmm.
But if it rained here,
Mm-hmm.
it would just tend to have less. So this might be 20% H2O gas.
Mm-hmm.
Right, because here it, deposited all that same. So I guess if it didn't rain,
Then it's fine.
I guess it would be fine. You could just have the air go over here. I don't know. I can't think of another good reason, but I guess it would. So you tend to have plants where, yeah, I guess because he mentions there's plants on one side. So of course, if there's plants, it must be raining. You wouldn't just have, just because there's clouds doesn't mean there's plants. It has to be.
Right.
So it tends to rain over here, and therefore it tends to be dry over here on the eastern side.
Right.
So on the Rocky Mountains again, you have like California or whatever is on the one side, and then
Nevada.
like Colorado, or Nevada, whatever. And I guess I don't think of Nevada as having a lot of plants.
No, it's like the desert.
Yeah.
Vegas in the middle of nothing.
So what's on this side of the Rocky Mountains then? I don't even know. Oh, wait, no, I'm thinking of the mountains in California.
Oh, no,
The
not the Rockies. What do you think?
maybe they're the same thing. I don't even know. The point is that Denver or whatever is pretty dry and has
Right.
really nice views because there's not like a bunch of trees and stuff in the way.
Right.
It's just sort of a really barren-looking thing, and it doesn't rain very often, for example, etc.
Okay.
That's it.
Hmm.
But Denver does well anyway.
We
I'm
have
not
like
gonna
the
say.
redwood forest on the California side.
Yeah, there we go. Thank you. Good. Now on to why it's hot and cold.
Okay.
Now, of course, yeah. So you might think it's I might think it's because of the air pressure. I actually don't think, I haven't done the calculation, but I don't think it's, because I think the air pressure is not that much less.
Mm-hmm.
So I don't think it would contribute. You could compute it and figure out how much less it would be, but I would say the main reason is because the heat, so the air temperature is like the temperature right here, right? I'll call this T1, and this will be called this will be called T2. So air temperature is like right above the surface, but it's basically correlated with the temperature of the ground. So temp of air is roughly equal to the temp of the ground nearby, let's say. Because what the ground does, you have the sun shines all day on the ground, right? And then what the ground does at night is it's not like, oh, then it cools down. It actually re-radiates, because it's warm, re-radiates infrared radiation, which is, you can feel as heat. Now, you won't go outside and, it's not like intense, like you'll feel it. You can feel infrared radiation.
Feel it off like your driveway or something.
Yeah, you might, especially maybe like right in the evening, you might go and feel like your driveway, because your driveway would. So, for example, the earth, like dirt and stuff, is really deep, and it has a very sort of, I can't remember there's some equation that tells you based on the radiation you get in and some factors what the radiation you get out is. But the point is that like the driveway is very thin, and so it has a pretty quick turnover, basically. In other words, it gets warmed up all day, and then it re-radiates most of its heat pretty quickly. But the earth, like the ground, is really deep, and so like, how much of it gets warm, it's several feet down probably. That takes a longer time to radiate, and so you actually get this much more even, right? If the day is warm, the night will be warm as well. It's not going to be, obviously it's colder, but it won't be like, it won't plummet back and forth. It might do that in places like a desert, which is, I guess, for a whole different reason, which is probably just because there's not as much. The specific heat of water, as we've been talking about, is much higher.
I was going to say, isn't it?
Right, the specific heat of water is much higher than in air. It's relatively high compared to most like substances for its weight. It's like relatively high. So if something doesn't have a lot of water in it, you might also get the radiated, like the desert ground radiates a lot of heat.
Yeah.
But
quickly.
The air might not absorb any of that. So there's several processes that happen. The sun has to radiate visible light. So this is visible. And infrared, of course, too.
Right.
Mostly visible light into the ground. And then the ground, after warming up, being warm means it radiates heat. And because it's so sort of big and dense and stuff, and there's so much around, it tends to just heat the air. And if the air has enough specific heat, basically, heat capacity, I should say, it'll roughly hold on to it. However, if you go to the top of a mountain, this area here, it doesn't really have enough, there's not enough, mass here to really be warm in this region. Because down here, you got, the whole area to heat you up. So this is all very hot. And then up at the top of a mountain, I mean, you're really not going to get much heat from, the nearby areas. It's not going to create a big, dense layer of hot air.
It's not like the summit's going to heat up everything.
Right. The summit can, is going to obviously heat up something, but it's, obviously this is exaggerated. It's not literally stand on the, but I mean, it doesn't tend to make a stable cloud of air. It's not like a valley. A valley would be the opposite, where you'd expect the whole valley to be warm. Right. This could be,
It's encased in.
Exactly. And all the ground is radiating heat to the air here. Where here, all the ground is radiating heat sort of away, and if you're standing here, right, you're only getting, the air around you is only getting heat from the ground or in a few places, and it's sort of not, you know what I mean? That's why it's cold on mountains.
Right.
And despite being closer to the sun, it's a little well, it's not, is it really closer to the sun? It's 0.001% closer to the sun. It's not, it's like taking a step east and then saying that I'm closer to Japan than I've ever been.
You are.
And it's just yeah, but who cares? That's not really like, so saying that it's closer to the sun is like a little bit of a like, that not really. If you think of the scale, it's actually like you might as well say it's not closer.
Right.
So that wouldn't make it. You know, you could make a mountain hundreds of times higher than the highest mountain on Earth, and it will not be warmer because it's closer to the sun.
Right.
That has no effect.
Right.
You know, even if you're on Mercury, it wouldn't have, like, you need to be anyway, whatever.
Yeah.
So yeah. That's it.
Nice.
I guess that's all I have to say.
Total side note: have you seen the movie Aeronauts?
I've not.
Okay, they're like while you were racing this,
Uh-huh.
I'll explain it. They're like in a hot air balloon. They're trying to see how high they'll go.
Yeah.
And the scientist actor is saying, he's like, I think we're gonna get warmer because we're getting closer to the sun as we go up
Uh-huh.
higher. So I don't know how that's tied in.
Well,
They did not get warmer.
Yeah,
If you're
I wouldn't think
curious.
so. Huh. Yeah, that's not.
I mean, it's like the 1800s.
Okay. Well. Have you seen the movie The Core?
No.
Where they go, it's like from along, it's really stupid. They have to, something in the center of the Earth stopped, like the magnetic field stopped because the core stopped spinning or whatever, so they had to like make like a thing that drilled down into the Earth.
Like respun it?
It was like an astronaut movie, but
Oh.
it was in the Earth,
Oh.
and they'd like ignite all these nuclear bombs to,
Get the cord to
and they all
spin
ended
again.
up dying. Spoiler. It had
Darn.
Aaron Eckhart.
Okay.
He plays, you know him?
Can you give me another?
He's from Batman. He's like the Two-Face.
Oh yeah.
Yeah.
Okay.
I kind of like him, but I don't like that movie. He plays a geologist. I like, come on. If any movie has a person who's a geologist, no offense, but I'm all set. I'm just kidding. Anyway, okay. So then, okay, what's number 8?
The 2 moles of an ideal diatomic gas that.
Oh yeah. So if you have a diatomic gas, well, we know we have the internal. It's on delta. Internal energy of a diatomic gas. Of an ideal diatomic gas is just going to be 5 halves kBT, right?
Mm-hmm.
Okay.
Right.
Good. And now this is for this number here is for 1 molecule
Okay, so you have to multiply
by
by 2.
2 times Avogadro's number.
Oh.
This is for 1 molecule. Yeah, not mole.
Oh, okay.
Yeah.
Okay.
So this, you have to do this times n Avogadro, and that would be 1 mole, and then times 2 for 2 moles, and that would give you the internal energy. And then what are they? Sorry, I have pictures, but I don't remember what the question was. Something about.
So he asks the equipartition theorem.
Yeah.
What is the total internal energy?
Yes.
And then what is the molar specific heat at a constant volume?
Oh, okay. So the molar specific heat at constant. Oh, that's a V. That's CV, I think.
Yeah.
So CV is actually defined as delta dE over dt. That's the definition.
Times 1 over n.
Yes. Thank you. Because it's per mole.
Mm-hmm.
Yes. So sorry. Let's look at units. That's important. So the units are going to be joules per mole Kelvin, right?
Right.
Because joules per Kelvin would be specific heat or heat capacity, or I don't know, whatever the words are. I don't know, but it has this units. So we know we have to divide it by moles too. So dE dt is just going to be 5 halves kb times n Avogadro times 2. And we're not going to multiply it by. We're going to divide by n. This. Okay, sorry. This n is 2.
Okay.
Because it's 2 moles.
Oh, okay.
So, you can find the internal energy for the 2 mole system, but when they ask the molar specific heat, we obviously want to do it for 1 mole. So we have to basically divide by 2 to get back to this.
Okay.
So this is going to be, I think that's just the whole thing. And they say at a constant volume, but that's what this is. So you don't really do anything special to get a constant volume.
Okay.
There is a thing, so I should mention that there's a thing, CV is generally what we're going to use for specific heat,
Mm-hmm.
but there's also a thing called CP, which is for specific heat at a constant pressure. Don't worry too much about it. It won't come up much unless, basically the only places you use these is in E equals mcv delta t, and then you might also use, delta E. And delta would be mcp delta t. So this would be the same. These are both valid expressions, except, of course, it depends on if you have a constant, if you have a changing volume, you'll have to use this one. And these are just numbers you look up. They have the same units, as you can tell. It's just that sometimes you might have to use the other one. Almost always, though, you use this one.
Okay.
Because it's a long story, but you'll see. It has to do with those ensembles I was talking about.
Oh boy.
Yes, it's very exciting. Okay, so that should be good. And then they ask you something about doubling the volume or something?
Yeah, if Q equals 3,000 joules of energy, and it's added to the gas as heat with the volume kept the same, what is the new temperature? What is the new pressure? What is the new internal total energy?
At a constant volume, they said?
Yeah.
Oh, okay. Oh, then if Q is 3,000 joules,
Mm-hmm.
well, delta E is Q minus W, right? Is the first law?
Yeah.
Okay, there's no W because the volume is not changing.
Right.
And so delta E is Q, so you get Q equals, which is 3,000 equals M CV delta T. And then you could solve for delta T.
Cool. All right.
That's it.
Yeah, and then what is the new pressure? Oh, I guess you just plug that in.
Oh, the new pressure. Then you could do. They told you. Did they tell you the original temperature?
They told us the original pressure, yeah.
The original pressure.
Mm-hmm. And the original temperature. They told you both.
I mean, I'm really tempted to use this somehow.
That's what I was thinking too.
But can you? Oh, you can, because you can solve for V. If you know initial, you know this and this, right?
Right.
Oh, okay. Then therefore you can solve for VI.
And then that's kept the same.
And this is kept the same, exactly, and then
Right.
you could plug it back in. Yeah, okay. Sorry, I didn't write it down, and I was like, why didn't I write it down? It's because I wouldn't write down PV with NRT for the 5th time. Anyway.
And then
and then something about doubling the volume.
Yeah, is allowed to expand isothermally until it's twice its volume, and then what's the total internal energy, how much work is done, how much heat is added.
Yes, so if it's allowed to expand, it's allowed to expand
To twice its volume.
isothermally.
Mm-hmm.
If it's isothermal, it means delta T is 0, of course. And we know that delta E is mc, I mean, I guess it would be P this time, but it doesn't matter because it's 0. So delta E is 0.
Mm-hmm.
Well, that's a little weird because we know that delta E is also Q minus W. Well, that just tells us that Q equals W. And W is
So the total internal energy would be 0?
the change in internal energy would be 0
Oh, okay.
because it expands isothermally.
So when it says the total would just be the same as the step before, I guess.
Yes. That was the first part? And
Yeah.
then the next part says, what is the heat or something?
So it asks for total internal energy, specific heat, and then what's the new temperature and pressure and total internal energy, and then it's allowed to expand to twice its volume. What's the total internal energy? I don't know if it means like after it expands or after the heat is added, or if it's like the original equation he gave us.
Yeah. We definitely have this.
Right.
For iso, this is for iso. Well, I'm not gonna write it. It's isothermal.
Mm-hmm.
And somehow. Oh well, they don't want the new pressure, right?
No.
Oh, okay.
Just the energy, work, and heat added.
Well, work is 0, right? That's not true.
No, well, I think work and heat,
right? Right. Oh, well, there's, of course, okay, sorry. There is work because you had to pull it to expand
Is
it.
this your like EQW diagram that you made last weekend or Saturday? Or no, is this something totally different?
The what diagram?
Your like EQW
Oh,
chart that you
um,
made, or is this?
Yeah,
is this different?
maybe.
No, that's never mind. That's.
Oh, not this question, but
that
maybe
was-
you
that was
could use
something
it.
else.
Hmm. I'm just a little concerned because the pressure is obviously going to change.
Mm-hmm.
Oh, okay. Well, okay. I see. We could find, so now that the volume V has doubled,
Mm-hmm.
V went to 2V. So we could find, and we know the temperature is the same, so therefore we could find P went to, well, it went to P over 2. It's a spoiler. But anyway, it did. So the pressure halved.
Right.
This is why I was a little concerned. This is why I thought that the,
Right. So how do you find energy?
so the work should be like P dV. And P is nRT over V dV from V to 2V. I'm using notation a little bit because I shouldn't write. I'll just V naught then, 2V naught.
Yeah.
And this is going to be nRT ln of 2. Okay, so this is, okay, so I guess it's just this.
Okay.
This is the work, but it's also the heat.
Okay.
And now if this is the heat and you wanted to find the, that's it. This doesn't apply anymore.
Okay, so you'd get heat, and then heat and work are the same, and then you just add those together to get the energy?
To get the total energy, you would subtract them, but then it would be 0. Because the energy is 0. Yeah, change energy 0.
So, okay.
So if you ask you about the final energy, it would just be the same as the energy before that.
Okay.
Which would be
Like
3,000 joules, I guess, right? Or whatever they did.
Yeah, like
whatever they did before.
Original, like in A or in C? That's what I'm
Oh,
confused
I don't
about.
know. Don't worry about total energy.
Okay.
Just as long as you do this, I'm pretty sure this is right. You should check this. This seems a little, I guess it's fine.
Okay.
It's just T naught because it's a constant. Anyway.
Alright.
Okay.
The next one is the mercury inside a glass tube.
Oh, yeah, okay. So we did that one last time.
Right.
Yeah, it had to do with, and there was like really annoying engineering
It was very
thing
annoying.
about how the glass expands and ooh, and yeah. Okay.
Mm-hmm.
So I don't want to do it again, but yeah, it just has to do with the changing volume. If you have some parameter that tells, it's just the Young's modulus thing all over again. A lot of these, as you'll notice, a lot of these are like the same thing, but then they use different words.
Mm-hmm.
So it seems like, oh, cool, but it's the same. Mathematically, it's identical to
Right.
the bulk modulus type thing.
Okay.
Bulk modulus, and then for the glass expanding was a Young's modulus problem, but it's a parameter that tells you how the length, the ratio of the change in length over the total length, which is a dimensionless parameter, is equal to, some modulus or whatever.
Alpha delta T.
Right, and you have to look it up for a proportional to the change in temperature, I should say. And when they derived it in the book, of course, they derive all of these linear relationships by Taylor expansions, because in real life, nothing really is linear.
Mm-hmm.
Like nothing really has a linear relationship. They just approximate it in a Taylor expansion. So if you see in the book that they do a derivative with respect to t, and then they use the first term, whatever, that's the Taylor expansion. So
Okay.
anyway, okay. So there's a bunch about entropy, right?
17 is next.
17 and 18 are both about changes in entropy after things happen, right?
Yep.
Okay. So, let me. So first of all, the easiest entropy for the change in entropy due to melting is equal to. Let me write this. This is the actual equation for entropy. This is the infinitesimal. All these are infinitesimal equations, right? Technically the first law. This is actually the first law is v dp plus t ds, or you could also write p dv and s dt. You just get a minus sign because of integration by parts, right? Which is also called the product rule. Anyway, you could there actually might be a minus sign here. I don't remember. There probably is because it's minus work. Anyway, whatever. Now I'll just make a brief comment, which I don't think we'll need to use this fact very much. But this is called the idea that this is equal to p dv, let's say minus s dt, and then you could of course pick any combination, right? The fact that the infinitesimal variables in this case are v and t, this is called an ensemble. This is called the VT ensemble, and there's names for them, like the Gibbs ensemble, the I don't know. I really don't remember any of the other ones. Anyway, there's name. You can look them up, and there's actually another term here, mu dn, which is not used very often. We won't use it, I don't think. This is the chemical potential, and this is for a changing number of. So now PV equals nRT now has a new variable called n, which it's not a new variable. It's still a variable, but we just consider it a constant for all these. But if you have a system that is not closed, so these are all we're doing we're doing isolated systems and closed systems, but we're yes, for isolated systems, this is 0 and this is 0. For closed systems, just this is 0.
Okay.
And for open systems, then they're all non-zero.
Okay.
But we're always going to do at least closed. And that's it.
All right.
All heat engines, by the way, are isolated. Oh, sorry, that's not true. Never mind. Sorry, forget I said that. Okay, let's move on.
Yep.
So anyway, these are called ensembles. This would be the PS ensemble. You can see there's 4 here. If you add the other term, there's actually 6, and they all have different uses. Just anyway, that's just what. But you could write the first law like this, like in infinitesimal form. Anyway, the point is that this is the infinitesimal form of entropy. And it kind of comes from this, the fact that S, well, anyway, we'll see. And so for melting, now melting is now I'm changing it to delta because I'm doing a finite amount. Delta, and you notice this T in general, it's not constant. But during melting, it is constant. It's just T melt, right?
Right.
And then up here would be the change in heat due to basically the change in heat of a system that is melting. So this would be L, right? It would actually be like M times L. This is fusion. So L is latent heat of fusion, right? Times, and whatever the dimensions are, maybe it's the molar ones, you do it times moles, whatever it is. The point is that up here, this is the actual heat of fusion. This whole thing is the heat of fusion, which is this, and then divide it by the melting point. And then, of course, you can do exactly the same thing for vaporization, same thing.
Right.
So this is an easy one. The other ones are a little harder because if you integrate both sides of this, it's not so easy. Like if you have, and I'll just put a delta here, even though we've already integrated, because we're just assuming it starts at 0. And what if we had something like, let's say we had something heating or cooling. So heating or cooling will get like a solid or liquid. First of all, solids and liquids, doesn't matter. Because solids and liquids don't have volumes that respond to pressure.
Right.
Or pressure that responds to volume. They do not obey the ideal gas law. They don't have any of that. So anything that's a solid and a liquid, even if they tell you the volume, this is a hint for the problem about ice. The problem about ice that talks about the volume of the ice and the air pressure, that is not, as far as I can tell, and there's a chance there's a chance I could be wrong, but as far as I can tell, that is all nonsense.
Okay.
And it's just to throw you off, because anytime anyone talks about pressures and volumes, they're always only talking about ideal gases.
So that's
Okay.
14.
Yes, solids and liquids like ice melting,
Mm-hmm.
the volume change does not enter into any of this. There's only if you have this many moles of water
Yeah.
and this many moles of ice, there's exactly one configuration, like one volume that each of those could take up.
Right.
You don't get to choose.
Right.
Right. So they don't respond linearly, and so they can't be written as a linear differential equation like this. Anyway, so the point is that for melting, we have this, and this is actually dq, of course. So really the first law can be written as dE equals dW, let's say minus dW plus dq. This would be the differential form of the first law. And again, now to write, the choice to write dW as this, as opposed to pdV, is the ensemble choice. Anyway,
okay.
But this is the most general one. Now, of course, if we have something if we have something changing in temperature, let's say we have water at 100, let's say we started with water at 0 degrees Celsius and it went to water at 100 degrees Celsius. I'm just making this up. And it's just liquid water the whole time, so it doesn't change phase or anything. What would we do? Well, we'd have to say the change in entropy is therefore going to be equal to the integral of the differential heat over the temperature. Now, what's dq? Well, we know that dq is actually equal to dE plus dW, I guess. And we do actually also know that a separate thing we know is that dE is mc dt. This is like a sort of separate thing we know. And we know for solids or liquids, or for gases if the volume and pressure are not changing or something like that, then we know this is 0, and so we actually know that this is actually equal to dE, which is mcv dt. So CV would be constant volume one, whatever. I'm just gonna keep writing CV even though, whatever. So that's this. MC are constants. This is dt over t. Right? And what is this? This is just mcv ln of, and now let's say it started at t0 and went to t1. Right? Plug it in at the final position, which is t1. Subtract when you plug in at the initial position. When you subtract logs, you could just write it as the division of their arguments. So this is the change in entropy for something being heated or cooled. Doesn't even have to be it's not one way or the other. I mean, if you flip these, if you say it's cooling instead of heating, it's the same as just flipping these, and then it's fine. Yeah. Actually, you can kind of see that flipping. So if you take the inverse, so ln of x inverse is equal to minus ln x is a math fact. So if you take the inverse of this, meaning you instead of heating something, you cooled it, we would actually get just the negative of the entropy.
Okay.
So we're, of course, that's it.
Cool.
Which
makes sense.
Yes. What else was I going to? Oh, also, what if? Okay, here's the other thing I was going to tell you. What if? So T1 is your final temperature, and let's say you're cooling it, and we'll say T0 is 300 Kelvin, doesn't matter, and let's say T1 is the final temperature is 0 Kelvin. Okay.
Cool.
Let's just say we wanted to get something absolute 0. What happens when we plug that in here? That would be 0. So this is all 0. What's the natural log of 0?
1. No.
So the natural log looks like, okay, it's just on the internet forever.
Great, love that.
ln of 1 is equal to 0.
Oh, okay. I missed it.
And ln of 0 is undefined. It's like it approaches negative infinity. Yeah. So how much entropy would we need to change by to get to absolute 0? We need to decrease by an infinite amount.
Yeah.
So that's another, I guess there was another part, I think, or maybe he asked in class, why can't something be absolute 0? This is another example, is to actually cool something to absolute 0, you would need to decrease by an infinite amount of entropy, essentially.
Right, yeah.
Or I guess a better way to put it would just be that it's impossible because it's undefined. I shouldn't even say minus infinity.
He doesn't.
Well, I guess I could just take the limit of this. So if you wanted to write it in math, you could say limit as t1 goes to 0 is minus infinity. So
Okay.
anyway,
Yeah,
Okay.
You're getting past my knowledge base,
well,
clearly. I appreciate it.
hopefully it's not in the homework. Also, so here's another one.
Okay.
And I'll just go through them. So hopefully I'm just trying to like do the common denominator of these problems
Mhm.
because I don't want to like actually, of course, I don't want to do the numbers obviously, but I also just don't want to like just do them in order because I just think the pieces are important. Because if you write down all the pieces and you know how to do all the pieces, then you can do all the problems like
Right.
on the tests and stuff. So I'll say this is for heating and cooling. So this is change entropy for heating and cooling. What about change entropy for volume changes? Okay, and let's say, so now I'll say this side is going to be isothermal
Mhm.
volume changes. Okay, because there's entropy. So of course, as if you heat something up, you're increasing its entropy, right? If you cool something down, you're decreasing its entropy. That's what makes sense. But if you heat something up, you can think of the increasing entropy as just, oh, it has more disorder, right? That's how the sort of casual way to think about it is just it's disorder. But what about if it's the same temperature, but you just allow it to be in a bigger volume? Shouldn't it be more like you would expect it to have more entropy, right? Because it still has more disorder. It's just instead of having more disorder because there's more, like it's more excited and there's more energy, like higher temperature, it just has a bigger space to be in. And that has more entropy. And so how do we figure that out? Well, if it's isothermal, then dE is 0, because dE is mc dt.
Mhm.
So dE is 0, but dE is also q minus w, sorry, dq minus dw.
Oh, yeah.
And now dq is not going to be 0. So this is a little thing that I think people are confused by. When I say people, I meant me, like when I took this class. But people think, oh, isothermal means the heat is not changing at all. But isothermal does not mean that. It means temperature is not changing. So dE is not changing because this is the definition of temperature. E is the definition of the internal energy is average kinetic energy of molecules.
Right.
So isothermal literally means that dE has to be 0 for a process. But dQ is the amount of heat that's going into something. The heat is actually not going to be, the change in heat is going to be non-zero for even for an isothermal process.
So like if it gets bigger, you add heat.
Yes, you would have to. Otherwise, the internal Otherwise, the internal energy would decrease.
Right.
Right. And if you want to keep it constant, you're going to have to compensate by adding heat. That's another reason why there was a minus sign here. Because
Isn't that like a thing in the Carnot cycle, like the top
Yes,
two
yeah, yeah,
are
yep.
isothermal?
Exactly.
Okay.
Right. The Carnot cycle, the two of the pieces
Mhm.
have adding and subtracting heat.
Right.
Right. And the other two have adiabatic things, so the heat is going to the heat's not going to change, but you're going to be compressing, expanding. So, yes, but the temperature then changes because if
Mhm.
this is 0 and it's changing its volume, which it does in the other part of the Carnot cycle, then this must change. So therefore,
Right.
the temperature has to change by that.
Okay.
Okay. So now we have this, and now what was I talking about? Oh yeah. So now we have that dq is equal to dw. And delta S is still going to be integral of dq over t, right? That's the definition. Well, this is the definition, we take the integral of both sides. But now dq, I can just instead write dw, right? Because it's the same thing. What's dw? Well, dw is going to be, now what's going to change? V is going to change, so we should probably do p dv. Did I get the sign right? I'll just pretend I got the sign. I think I got the sign right. P dv.
Mm.
Now, well, we can't really do this because we have. We can't really do this because we have P and T, which are not V. So how do we do that? Well, luckily we know. Sorry, this is an ideal gas. I should have mentioned that. These are all ideal gases. Sorry, this does not have to be an ideal gas. This does because I'm talking about changes in volume. So of course it has to be. Therefore, we can use PV equals nRT. P over T is right here. So let's do this.
Mhm.
Right? I just rearranged it. So P over T is actually equal to NR times dv over v now. That's it. And now we just have v initial, v final, and we get NR natural log of v final over v initial. So this is the change in entropy due to something expanding. And we can just check the if something expands to get bigger, we'd expect it to have more entropy. So therefore, if v final, let's say, is twice v initial, what would we expect? Well, if v final is twice v initial, this becomes 2. Ln of 2 is a positive number, right? Ln of anything greater than ln of anything greater than 0 is a wait, sorry. Yeah, okay. Sorry, why am I? Yes, okay. Sorry, I confused the sentence in my head. The ln of something greater than 1 is positive. The ln of something less than 1 is negative. So we'd expect that if something gets bigger, that means that this number is positive. Sorry, this number is greater than 1. So therefore this is positive, and therefore the change in entropy is positive.
Okay.
That's it.
Makes sense.
Now there's one more thing. Actually, sorry, one subtle thing is that if instead of this work, let's say the pressure changed. So say the pressure decreased. That might be the same exact process. It might be that you got bigger because the pressure decreased, but we don't know about we could do the exact same thing. We could put this as VdP. This is actually going to be minus VdP though.
Okay.
The reason again is from the product rule, because technically we have D or integration by parts, right? This D is like it's a real math thing that I'm not explaining in a precise way.
Okay.
But because of integration by parts, if you put the thing on the other thing in an integral, it becomes minus. Anyway, so there's a minus, and now we could do this exact thing, but instead leave V here and put P down here. Same ideal gas law. And now we have NR, VT, and now this step is going to be dP over P from PI to PF, okay? And then we get ln of, it looks identical, minus, and it looks identical, but we have a minus sign now. So that seems like it's going to screw things up, because we still have P final on top and P no. So if we double the pressure, what does this mean? If we double the pressure, that means that this is going to be a positive number. Sorry, this is going to be greater than 1, therefore this is a positive number, therefore the answer in change of entropy is negative. But does that make sense? Oh, wait a minute, yeah, because if you increase pressure, you should expect less entropy. So it actually does work. So the fact that you get this minus sign is actually very important. And also, because of the rule that I erased about logs, we could get rid of the minus sign and just put pi over pf.
Right.
Because, right, minus log, so the other, they would just be minus log of x equals ln of x. Same thing I wrote before.
Right.
So all I'm doing is just absorbing the minus sign into it's generally good whenever you have logs to not put minus signs in front of them, because it's just a little easier to, it's much easier to see that, oh, therefore if I double the pressure, I'm having a smaller than 1 number here. Like, it's just easier to see than to remember that there's another minus sign. So
you'd recommend pi over pf?
I'd recommend writing P over PF, and if you're writing the V version, VF over VI in that case. That's it. You cannot do both of them at the same time. Careful.
Sorry.
You cannot do both of them at the same time, and the reason is because they're not independent variables. They're dependent on each other. That's why we can't write, like, we have to choose one or the other. We have to choose this one.
A certain ensemble.
We have to choose a certain ensemble. We can't just, like, be like, well, what if they're both changing? Isn't it like the product rule where we have VdP plus PdV, right? We can't have that because they're not independent variables. So we'd be sort of double counting the same process, right? Like, just like T and S are kind of, it's a little harder to, well, that's a stupid example. Anyway, that's actually why we plot P over V on diagrams, because one is dependent on the other. So if you know a state here, you can predict things about it. So anyway, Now, the thing I actually wanted to say, the last thing I want to say about this is let's go back to VF over VS. Let's go back to volume again.
Right.
Both sides of the board, the reason I left it here is because let's say we have a gas, so it can expand in volume and it can change temperature. And let's say we have a gas that has done both things, but they don't tell us what happened. They just tell us a gas had an initial temperature and initial volume. I guess I should put V naught and V1 to be consistent with that. And let's say it had that's not a 1. Let's say they had a T naught, an ideal gas at T naught and V naught, and then later it was at temperature T1 and volume V1. What is the entropy? How much entropy was entropy increased or decreased or whatever, right?
What happened to entropy?
How could we do that? That seems like, well, if they didn't tell us like it was isothermic or it was adiabatic or it was isobaric or whatever for part of it, and then obviously it can't be isobaric or isothermal because the point is that there's a fact about S
Mm-hmm.
it's called a state function.
Okay.
What else is a state function? Internal energy is a state function. Temperature is a state function. Volume is a state function. Pressure is I guess they're all state functions.
Okay.
I'm just
gonna
making
say,
sure
you're
in my
listing
head.
off a lot here.
Yeah. Q is a state function.
Mm-hmm.
Sorry, Q is not a function. Q is a quantity. I wouldn't say work is a state function either. Okay, maybe I'm confusing myself. Maybe they are. The point is that S is a state function.
Okay.
Which just means that if you say like, let's say I'm plotting S versus T, and some like this is like a diagram, whatever for some process, and let's say I say it did these squiggly lines, and then it went up to here. How much did entropy increase? All you would need to know is this much here. That's what it is. It just increases like this. So I could just pretend that first. Well, maybe this isn't a good diagram. Let me not write labels on it. Let me just say that in some space, it went from here and then went to here. We could actually just say that it only depends on the position, the final position and the initial position.
So you don't care about all the fluctuations.
Sorry, I should say V and T.
Okay.
And each V and T value of an ideal gas has an entropy, and this has an S plus delta S. This is what I should have said. I'm sorry. I wasted it. So every point in V and T space, you can find the volume, of course, or the pressure, of course. So this is some entropy at some point, and then it does some weird. You play it like an accordion or whatever. I don't know. And somehow it's at this other place.
Mm-hmm.
The fact that it's a state function means that the delta S here only depends on its value of T and its value of V. So this is V1, this is T1, and this is going to be T0, and this is V0. So in other words, the path that it took to get there doesn't matter at all. Just like gravitational potential energy is a state function, right? You can go on a roller coaster, and they can tell you, it did all these corkscrews and flips and stuff, and it ended at the same height that it started at, and there was no energy added. What is its potential energy? You would just say it's the same as where it started, so the change is 0. You don't need to know about the path, right? Friction is not an example of this. This is very similar to a conservative force, right? So remember, a conservative force is kind of like this. Now, this is not force, by the way. But a conservative force means something that has a potential. So every conservative forces have potentials, just like gravitational potential energy, or gravitational force has a gravitational potential energy we can talk about. So the fact that we can do that means it's a conservative force, and it only depends on the height. That's the only thing that matters for gravitational potential energy. You don't need to know what happened before. You don't need to know. You just need to know the difference in height, basically, if you want to find the change in gravitational potential energy. Same exact thing with this. You only need to know the changes in the two variables. So the point of all this is that we can just pretend that if an ideal gas started like this and ended like this, we can pretend it went all the way here, exactly at the same volume, and then all the way here at the same temperature. And we'll get the right answer. What that means is that we just add these together. So if they tell you an ideal gas changed its temperature and its volume, and you have to find the total change in entropy, we just add them together. Now, of course, they might not be the same sign. If you increase the temperature and decrease the volume, then they would, they might subtract each other. Actually, of course, if they cancel out, if they're exactly equal and cancel, you would have an adiabatic process.
Right.
So if you let something expand, right, and then it cools down while it expands, and if it's an adiabatic process, that means that you're at any point in time compared to where you started, your final temperature and your final volume will be related such that these cancel out.
Yeah. Wow.
So, which is kind of interesting.
Mm-hmm.
So we've been talking about adiabatic, and I feel like adiabatic is always very like, well, it means that the entropy is like doesn't change, and it's like, okay, like whatever. It just kind of means it's like you don't have an intuition for it, or like there's no math about it. The other ones have like equations.
Right.
The other ones have like, oh, I can do this integral, whatever. But this one actually has one, which is now that we have expressions for entropy, we can just literally make them cancel out. And you can see that if something had a fixed volume and only changed its temperature, it could never be adiabatic, because how are you going to make this 0 unless they're the same temperature?
Right.
And nothing happens. So you have to have something to cancel it, and the thing is this. Of course, same exact thing you could do with pressure.
Right. Okay.
It would just be a different variable to express the work in. And these are the only two, right? There's only two terms here.
Yeah.
This is from heat, and this is from work.
Mm-hmm.
So there's only the two things, unless we're forgetting about the chemical potential, all that stuff. These are the only things that can cancel. So an adiabatic expression is defined by temperature and volume of pressure. And if you want to get even fancier, okay, this is the last thing I'll say about this, and we'll see if more questions. But so like in addition to this rule, I'll say n. I won't say n. I'll say, what's a letter? A.
Yeah.
A ln x. A is a number, any number, is equal to ln of x to the a. And actually, you can kind of see if a is minus 1.
Yeah,
It's just
I was
this.
gonna
Yeah.
say that makes sense.
So, in other words, 2 times ln x is the same as ln of x squared, right? Again, it's common practice. It's also, well, anyway, okay, I'm going to do it. But, and so if I tried to actually literally equate these to each other, if I set them equal, well, sorry, set them equal, which just means I'm adding them and putting a minus sign here. So that means I actually want to find the equation for an adiabatic process. So let's actually do that. I didn't even plan on doing that. This is even more fun than I thought.
Oh my gosh, look at you.
Whew. All right. So if delta S is 0, this is adiabatic. That means that mCv ln of T1 over T naught has to equal nR ln of V1 over V naught. We could write this as, so I'm going to just destroy this board a little bit. Just erase all this. This means that, well, now let's do this trick. And so now we have
T1 over TO to the MCV.
Exactly. So it looks really weird now, but just wait a second. And then we have also ln of V1 over V naught. This is raised to the nR power. Actually, you know what? I'm gonna do something else. I'm gonna move these things over here. So I'm actually gonna write over MC. I'll drop there's a V here, but I'm not gonna write it because it's annoying. But sorry, it would be exactly the same. We could do the other way. I will only want one side to have these things. Now, what do? Well, we have ln of something equals ln of something else. We could talk about math reasons why we couldn't just cancel the ln's. And the reason is because that doesn't mean anything. But the actual math reason is because natural log is a monotonic surjective function. Sorry, injective function. It actually is not surjective. An injective function means one where if two outputs are equal, the inputs must be equal too. Because you could imagine like x squared, just because the outputs are equal doesn't mean you could have like minus 2 and 2 have the same Sorry, this is a math tangent.
So like T1 over TO equals V1 over
Exactly.
VO.
That's what. In other words, I don't want to just do this and pretend that we're canceling ln's because that's not a mathematically sound thing to do. We're only allowed to do that because ln's of things are only equal to each other when their inputs are equal.
Okay.
And the name of that property is called injectivity. If you really wanted to. No.
Do a deep dive on it.
Yes, you could. So there we go. This is it. Isn't that weird? So this is the defining property of an adiabatic thing. You could even move T naught over because T naught is probably going to be given or is a fixed thing.
Right.
And you could say, what's the temperature? I adiabatically expanded something from this initial volume at this initial temperature. And
What's the final temperature?
yeah, hold on. Now I'm a little nervous because you would need to know the final volume. Oh yeah, of course, because otherwise you don't know how long it's been. Yeah.
Right.
So you need to know. You'd say the final volume. You could find the final temperature.
And vice versa.
Yes. And you could now if you Google adiabatic ideal gas law or whatever, not ideal gas law, adiabatic relationship, you'll probably find this expression. It might look slightly different, but it'll basically be this expression.
Mm-hmm.
And the problem is that a lot of times, if you go online, I'll often see like sheets where it lists all the possible. Like I put P's in here, and it's just like it doesn't mean anything unless you can see it done.
Mm-hmm.
And also, you probably need to do it like once in your whole life. Because,
so if we were going to use pressure, it would be PO over P1.
yes, everything would be identical, of course, but we'd have PO over P1. Yeah.
Okay.
If you really wanted, you could leave the power of MC on the temperature side and the NR over here if you wanted. I just figured it would make more sense on one side, but
That makes sense. All right.
all right.
Like you kind of asked. No, he doesn't.
Um, yeah, well, that's about mixing water, right?
Yeah.
Okay. I can say one more thing about that,
All right.
which I have written.
Sweet.
And then I dare you to think of anything about entropy that you want to hear a single more word about. Because I don't think you will.
I doubt I could think of something, so. I don't think.
I hope you don't, because I probably don't have anything else to say.
Yeah, no, I don't think I'm your gal for that,
but-
so that's more of an Ashley thing.
True. Oh yeah, I'm sure she would. So let's say you have mixing water. So let's say, and I'm not gonna like mixing anything, but mixing water. Let's say at two different temperatures. So it's not different materials this time. If it was, that would be fine. But I'm just using a specific case of mixing of the same thing, the same material at different temperatures.
Mm-hmm.
ds is of course equal to dq over t. But if we have we're going to have the change in entropy of the hot water plus the change in entropy of the cold water, right?
Mm-hmm.
So we have two, and forget about how much there is. Clearly, the total entropy change is going to be the change in these two. ds hot is going to be dq hot over T hot. Well, okay. I'm a little bothered by this. Hold on a second. I don't think this is actually right. I wrote this down, but I don't think this is actually right. Because ds hot should not be... Oh, sorry. Oh, this is fine. Okay. So this is fine. I have not integrated anything.
Okay.
So this is not a fixed number.
Right.
This is the temperature of the hot water over time.
Okay.
So if we want to actually solve this, we would have to integrate, and this would be the temperature of the hot water as it cools. T hot is going to cool to T equilibrium, and T cold is gonna cool to T equilibrium. So these are actually variables. So I should put like a T for time maybe here. I just want to show something that's not related to that exactly. To actually solve the problem, you would of course integrate both of these, right? But the cool thing that happens is that how much heat is, so this is an isolated system.
Right.
How much heat is the hot water going to give up? Let's call it dq. That's how much heat the hot water gives up to the system, to the rest. How much heat does the cold water absorb compared to that? It should, if it's an isolated system, it has to be exactly the same.
Yeah.
So the heat the hot water gives up is exactly as much as the cold water absorbs.
Wow.
That has nothing to do with how much there is. There could be 10 times as much cold water. Doesn't matter. Temperatures don't matter. This is why I wanted to do it abstractly, like as opposed to putting in like an actually solving or anything. Because that's an actually cool thing is that dq hot, I'll actually say is minus dq hot is dq cold. Because dq hot is giving, the hot water is giving up heat and the cold water is absorbing exactly the same amount of heat. Okay? Now, if I write this as, this up here as dq, just dq, so I'll call this dq. This is going to be 1 over T cold minus 1 over T hot, right? This is ds. Sorry, I'm going to erase this T because I actually just realized that this is an infinitesimal equation. I'm not integrating yet because I want to talk about ds is the infinitesimal change in entropy. Okay? I could leave T. This is still a valid equation. It's not like I'm doing something stupid. I'm just, if you wanted to integrate, this temperature would not be constant, but in the first instant that you mix the water, the very first instant, you are actually at T hot and T cold, right? Now we have this. Now what is this? Now actually you can write this, how else could we write this? Let me think. If we multiply this term by T hot over T hot, we'll get T hot over T cold, T hot. And if we multiply this one by T cold over T cold, we'll get T cold. So we'll get this, right? This is just an algebra. Now let's look at, what is ds then? ds is the infinitesimal change in entropy. Now even if we integrated it and evolved it over time, T hot is always going to be larger than T cold, right? Even at the point where they're equal, then it's 0. But it's always going to be higher. So this number is always going to be positive. This is a product of temperatures. Those are always positive. This is always greater than or equal to 0 for all times. Even if I kept them all as functions of time. This is always greater than or equal to 0. We just showed that ds is greater than or equal. This is the second law, right? So we just figured it out that by mixing this water, we're necessarily creating more entropy. Proportional to the change in,
Right.
Yeah, until they're equal, and of course then nothing, exactly. And that's the reason why, so if ds is greater than 0 for a process, it's called spontaneous, it's the chemistry word for it, a spontaneous process, and if ds is equal to 0, that's like equilibrium.
Yeah.
Right? And so this is just saying that if you put hot water and cold water in a cup, like you just pour them next to each other, they're going to mix. This thing is going to happen. Like it's not like there's a chance that they could separate. The reason that they are going, now it sounds like a stupid thing to say, but the reason they are is literally because of the second law. We just showed that the fact that they mix, the fact that heat is given up and received, is equivalent to the fact that the second law of thermodynamics is true. So the fact that something's spontaneous, that if we assume that a spontaneous thing is such that this happens, we've shown that it's spontaneous. And if you tried to work this backwards, you could actually if you negated everything here, you would get that. That's what if you had water and you wanted to separate it into hot and cold water, like by itself or something, I don't know how. let's say you want to do that, you would just basically say that the hot would have to get a plus amount of heat, and the cold would get a minus amount of heat. You get a minus here, and this number is still always positive, but you get a minus. So therefore, you get ds is always less than 0, and we know that's literally the opposite of the second law. That will never happen.
Right.
It's not just not spontaneous; it just doesn't happen.
Right.
Because entropy in an isolated system, entropy always increases.
Mm-hmm.
So therefore, so again, these are just taking obvious things like water mixes and changes temperature, and it does not separate into hot and cold water, and just showing that they're actually those statements are equivalent to this mathematical mysterious thing we've been talking about, which seems like a thing you have to memorize, but it's actually literally the same exact thing.
Cool.
And it's a cool demonstration that this number is always positive. There's a lot of cool math proofs and stuff that if you do like stupid number proofs for a long time, you get to realize certain quantities that are always positive because they're very useful. Because most quantities you don't know. Like if I just wrote a random fraction, could be negative maybe, I don't know. But this fraction happens to always be positive, assuming that hot means hot
They're
and
not.
cold.
Yeah.
Yeah, so. Okay.
I can't think of anything else having to do with entropy.
Okay. Sorry, I just mentioned for the video, to actually do the problem, you have to integrate both of these.
Okay.
And you have to figure out based on the initial, so this is not, well, it's still T hot, but now volume doesn't change, so you have to use Q equals M cat with a D. So D is, so that's going to be dt, so it's going to be like a natural log on this side, it's going to be a natural log over here. The masses are going to be different, right? C is going to be the same, but the masses are going to be different. So you're going to get slightly different amounts here and here. Sorry, this is a minus though. Oh wait, no, this is a positive. Yeah, okay, I think that's good. Anyway, and then you'll get like natural logs and stuff. But of course, you have to first find the equilibrium temperature, which is like from last week's homework. Like that's the last week's homework problem. Because you have to know that because they go from T hot to T equilibrium. This is T cold to T equilibrium.
Mm-hmm.
And the reason I say it's okay that this is positive and this is positive is because this one is heating up and this one's cooling down. So by the natural log, you'll automatically get that this one is actually going to be a negative entropy. But which is okay because it's part of a system with the overall entropy is necessarily going to increase.
Mm-hmm.
Isn't that fun?
Loads of fun.
All right. Do you have any more questions?
I do not.
All right.
At least not right now.
That's very exciting. Well, there's Wednesday too.